Welcome to the video about discontinuities. This is one part of a series that goes through how to graph rational functions. To start talking about the definition of a discontinuity, I want to remind you about what a rational function is. So here we have a rational function f of x, and it's a rational function because we have a polynomial in the numerator and the denominator, right? So I've written that down as a reminder that g of x and h of x are polynomial functions. It's just that one is in the numerator and one is in the denominator. So a discontinuity happens when there are values that make this function undefined. Well, how do you make a function like f of x undefined? Well, that's where you draw your attention to the denominator. So really, it's the x values that are making h of x equal 0 that make the function f of x undefined. And when we have those x values, we realize that that causes gaps in the domain and gaps on the graph. So to get into the different types of discontinuities, I want to also remind you about the restrictions that we've been writing down when we simplify rational expressions. So these restrictions are the things that are creating the discontinuity. So let's take a look at a rational function here. You might notice that it's already factored, and there's some simplifying that we can do. So if we could cross off the x plus 5s, right, we would know that there is still an x minus 10 in the numerator and an x minus 6 in the denominator. But we would also have to write down the restrictions. So I see two restrictions. The first one comes from the factor we crossed out, so x can't equal -5, or else f of x would be undefined. And we also know that it can't be 6, because if we plug 6 into x right here, the denominator would be 0. But it really turns out that you don't have to write that 6 down. Notice how if I looked at this function, I would know that there is a restriction of 6, right? This is still there. It's still visible in the function. Whereas the x plus 5s, they've been crossed off, right? There's no remnants of them. So that's why this restriction is really important to write down. And it's also the basis for why these two restrictions are actually very different. So the discontinuity at 6 is not the same as the discontinuity at -5. They're both discontinuities. It's just that they're not the same type of discontinuity. To demonstrate, I've actually graphed this for you. Now, in the coming videos, you will also learn how to make this graph. But just to help you understand, I thought that a visual would be very helpful. So you'll notice that at -5, we actually have this hole in the graph, and at 6, we actually have this asymptote. So there'll be two different types of discontinuities that we focus on in this video. However, there are more. So like I said, the two types of discontinuities that we're going to focus on, one of them is called an infinite discontinuity. And that's just a fancy way of saying vertical asymptote. We get vertical asymptotes when we have values that make the denominator 0. That is after everything has been simplified, right? Meaning that it's not coming from some factor that was eliminated. This is when the factor does not get eliminated when we're simplifying, okay? So here's a good example. We have this rational function, we factor it, and then we realize, look, there are these two factors on the bottom that aren't going to cancel out. So 2 and -2 are going to be those restrictions, and we know that these will be vertical asymptotes. They weren't canceled out. Okay, so we have infinite discontinuities. Another type of discontinuity is called a removable discontinuity. This is the hole. We get holes on our graph when we have values that make the numerator and the denominator 0. It has to happen in both, right? In other words, it's the factor that gets eliminated from the numerator and denominator when we're simplifying, right? So this is where the crossing off leads to a different type of discontinuity. So here's one that we have that can factor, and we can see that the x minus 1s are going to cancel, leaving us with just an x plus 2 and a restriction that x can't equal 1, right? These are very different types of discontinuities. We now know that there's going to be a hole. Now let's talk a little bit about how we figure out exactly where that hole is. The first part is coming from the actual restriction. So the x value of the hole is the restriction. Now to find the y value of the whole, we're going to plug 1 into what's remaining of that function. So I'm going to plug in to just this portion of it and realize that we get 3. So the whole is at 1, 3. So let's break this down a little bit more. Let's just focus on vertical asymptotes for a moment and see what's happening here. So those infinite discontinuities are called infinite for a reason. So I've come up with that same rational function that we just worked on, but this time I want to look at the values that surround each of those discontinuities. So we know that -2, right, is a discontinuity. If we plugged it in, we'd get undefined. So I've plugged in 2 values to the left of -2 and 2 values to the right of -2. Extremely, extremely close, right? Take a look at what happens here. At -2.1, the y value is 13. We go a little tiny bit closer to -2, and we have this huge jump, right? We jumped from 13 to 126. Now let's take a look at the right side of -2. At -1.99, this time it's at -123. So look at this big difference. These values were positive. These values are going to be negative because look at that next one, right? So not only is there a huge jump between these 2 values and these 2 values, look at the jump between these, right? And we know that these are on different sides of the grid if we were to plot them. Let's take a look at the next discontinuity. Let's see what's happening there. If I plug into the left of 2, I get some values that are positive, 8, and giant jump, right, 75. And then on the right side of 2, there they go again, in the negatives to -74 and -6. So let's plot those, and you'll see, right, here are 2 on the left that are positive, 2 on the right that are negative, same thing here. So we can start to see why we're getting vertical asymptotes. Something is different on the left side of that value compared to the right side of that value. So if I actually make the graph for this, it's going to look something like this. It has 2 vertical asymptotes. All right, let's take a little bit of a deeper look at removable discontinuities, or the holes. So here's that example that we talked about, where we found that there's going to be a hole, right? And the hole is going to be at 1. We even found the y value of the hole was going to be 3, right? Now take a look at this. I'm going to do the exact same thing. I went a little bit to the left of 1 and a little bit to the right of 1. So values close to 3, even closer to 3, but below 3. Now we cross over and look, now we're above 3, a little bit more above. So it's like we skipped over, right? It's like this should have been 3, but it couldn't be there because then it would be undefined. So the plot of that looks like we have a regular old line, right? Like we didn't skip a beat, except we skipped one tiny little point right here, right? So the graph winds up looking like this because we're graphing the line y equals x plus 2, but we're putting a hole at the point 1, 3. All right, so just to compare these two again, remember that when the factor remains in the denominator, we get this picture, right? And you can tell it's kind of all over the place. There's some going towards positive infinity. There's some points going towards negative infinity. That's what gives us a vertical asymptote, when the factor remains in the denominator. But when the factors are eliminated, look at how the points go in a nice pattern, right? There's some order to this pattern. When that factor is eliminated, we get the whole. Okay, now there's one more really big important idea I need to make sure we understand. Horizontal asymptotes are not discontinuities, right? I've only said vertical asymptotes and holes. Horizontal asymptotes are not considered discontinuities because they're not gaps in the domain. So please don't consider horizontal asymptotes in the same category. In fact, they're so different, the next video is going to focus just on those. We've separated them by video to make sure that you get that idea that they are separate things. So what you should be able to do from here is to look at a function like this. Here's p of x, and you should be able to determine what the discontinuities of p of x are. So I want you to give that a try. You could pause the video, see if you could come up with the discontinuities. I'll tell you right now, it has two. Right? Write them down, figure out what they are, and then start up the video again and see if you got it right. Okay, so to find the discontinuities, we would have to do some simplifying. We know that the x minus 1s will cancel, so that means that there will be a hole at 1 comma something. So I'm going to find that something by plugging 1 into what's left over. So 1 plus 2 over 1 minus 5. Notice I didn't plug it in here. These are gone. So we get 3 over negative 4. So the hole is at 1, negative 3/4. And I'm switching color for my other discontinuity, which is coming from right here. That means we have a vertical asymptote at x equals 5. So there are 2 discontinuities. All right, it's time for you to do some more practice on your own. Good luck, and don't forget to ask questions if you have them.